Welcome to UV Physics Academy. So here we are discussing quantum algorithms, and in this fourth part I'm going to discuss about this Deutsch algorithm. Okay, so what is this algorithm? This algorithm is used to identify whether a given function is balanced or constant. What is the meaning of balanced? For example, we have a function f of x. X is the input, f of x is output, let us suppose. So for half of the input values, f of x is giving a value, let us say 0, and another half of the values of input, f of x is giving, let us say 1. So then half input values are taking one output, and another half of the input values taking another output. So this is nothing but a balanced function. So constant means whatever the values of input, always the output is constant, that is either 0 or 1. So one more time, so balanced means half of the inputs let us say takes 0. Next, another half of the inputs takes 1. So constant means here we have for all inputs, that means always output equal to either 0 or 1. This is for all inputs, either 0 or 1. So this is algorithm, and okay, so if you want to solve this circuit, Deutsch algorithm circuit, first we have to know one most important feature, that is phase kickback. This algorithm depends on phase kickback. Let me introduce that. So phase kickback. So what is this? So for example, here we have 2 qubits. Okay, so let us say this is x, it may be either 0 or 1. Okay, so here we have minus, that is a diagonal basis. Okay, so and here I'm taking a C0 operation. Okay, so then this is nothing but this -1 as it is, it transfers the information from target register to data register. So that is a phase factor, -1 whole power x and x again. So in the place of C0, let us suppose we have some function, function similar to this. So let us suppose here we have some function, okay, some control operation. So here x is as usual, and this is minus a state. Okay, so here target register minus, but data register, some information of f of x is transferred from target register to data register. So that is -1 whole power f of x into x. So some phase factor will be there, right? So this is a phase kickback. So this algorithm based on this phase kickback. Now let me draw the circuit corresponding to this algorithm. Right. So let me write this phase kickback final result. So here we have initial state x, and diagonal state minus under this UF operation. So this is a -1 whole power f of x and x minus 1. Sorry, minus. So that's it. So this is the final result. Now this is the circuit corresponding to this algorithm. Okay, so here we have 2 qubits, and here let us suppose this is the 0. Okay, and here it is 1. So here 2 head mod operations are there. Okay, and after that here one more head mod operation, and after that measurement. That's it. Okay, and let me write one more time. This is x minus state, and under this unitary operation UF, so this will become -1 whole power f of x, x minus, right. So now let us solve this circuit. Okay, so here initial state is 0, 1. So now here you are applying a head mod operation, that is uh, two head mod operators operating simultaneously on this input. So then you will get, so h operates on 0, you will get plus, and h operates on 1, you will get minus. So I am not changing that minus because finally I would like to get a minus state, and I am going to rewrite this plus diagonal state as 1 over root 2 0 plus 1, so into minus, right. Okay, so now we are going to operate this UF, that means so let me write this. This is finally 1 over root 2 0 minus plus 1 minus. Now under this UF operation, now UF, that means this unitary operation is executed, then what you will get according to this formula. So 1 over root 2 as it is. Now in the place of x you have 0 here, okay, in the place of x you have 0. So this can be written as minus 1 whole power f of 0, 0 minus state as it is, but here in the place of x you have 1, so that's why a minus 1 whole power f of 1, so this is 1 as it is and minus as it is. This is after executing this unitary operation. That f is some a given function, we don't know whether it is balanced or constant. Now here we have two possibilities. So let me take, so let us suppose the given function f of x is balanced. So what is the meaning of f of x is balanced? So that means half of the inputs will take one value and half of the inputs will take another value. That's why I am assuming here we have function f of x. So output will be f of 0 or f of 1. So that's why what I am taking is f of 0 equal to 0 or f of 1 equal to, sorry, and f of 1 equal to 1. So you may get one more doubt. So shall we take like this, f of 0 equal to 1 and f of 1 equal to 0. Why not? Sure, you can take, no issue. So first let me apply this. That means your output will be f of x, that means either f of 0 or f of 1. So f of 0 I have taken 0, f of 1 I have taken 1. So if both are same, then we have to say that function is a constant. So in this case I have taken function is a balanced. Okay, now please take this and apply. So then it is 1 over root 2, f of 0 is a 0, then you will get a 0 minus 1, f of 1 is 1, that's why minus 1 whole power f of 1. Okay, so I hope you got it. This is a minus 1 minus, right. So now I am separating that a diagonal state, that is a diagonal basis state, that is minus, separately. So 1 over root 2, so this is a, sorry, 0 minus 1, sorry, minus 1, and after that minus. Now after this we have one head mod operation. If you carefully see here, the head mod operation is there. So then this is nothing but head mod tensor I. Okay, so I will operate on this minus and head mod will operate on this 0 1 state. Head mod will operate on this and I will operate on this minus state. Okay, So once the head mod operates on this 0 minus 1, so you will get 1. So because head mod operates on 0, 1 over root 2, 0 plus 1, and head mod operates on 1, this is 1 over root 2, 0 minus 1. So this is nothing but 1 minus. Okay, so once you make the measurement, so here you will get a 1 and here you will get a minus as it is. So once you make the measurement here, so the first qubit you will get 1. So this is a possible only when f of x is balanced. So now you can try this one yourself. If you take f of 0 as 1, here you will get a minus and here you will get a plus. Then I will take minus outside common, something like that. Then some phase difference will be there. So that's why finally f of x is balanced, we can write like this. So we always get either plus or minus 1, minus. Okay, so this is possible only when f is balanced. So once you make the measurement on the first qubit, you got this 1, then you got this 1, you can confirm that f of x is balanced. So this is f of x is balanced. Okay, so let us take another one also to understand this algorithm, but it's not no need actually. The reason is once you check this, so that is enough. If f of x is not balanced, it may be constant. Let us take the second condition also. F of x is constant. That means f of 0 equal to f of 1 equal to 0. So both inputs, that means 0 and 1, are having same output, or else you can take f of 0 equal to f of 1 equal to 1. Let us take the first one here. So then this will be, after taking this condition, f of x is a constant, so your output 1 over root 2, so both are equal to 0, that's why here this is plus 1 and this is also plus 1. So finally this is 0 plus 1 and minus. Now after this we are operating this head mod tensor I. Okay, so on the first qubit state we are operating h and the second I. Then you know already this one, so this after this operation will get 0 minus. Oh, if f of x is a constant, if you measure the first qubit here, will make a measurement, then you will get 0. So if you get 0, then f of x is constant. That's it. Okay, so once you make a measurement here, so you'll get a 0. So this is Deutsch algorithm. Okay, so to find whether the given function is constant or balanced. Now again here I'm another method I'm going to discuss, that is a decimal state notation. So personally I feel it's a little bit easy to understand what is happening in this algorithm or in this quantum circuit. Especially this decimal state notation is used to solve the quantum circuit easily. So in the earlier videos I have uploaded one single video of how to solve quantum circuits in another by using a new method or something like that. So I request you please watch that video. So definitely you can solve any quantum circuit easily. Okay, so let me take that. Right, so here we are going to solve this Deutsch algorithm circuit by using a decimal state notation. So I feel that is a little bit easy to solve any quantum circuit by using this decimal state notation. Let me explain briefly, but detail I have already explained in a video, that is solving any quantum circuit by using a new approach. Okay, so here we have, let us suppose one qubit state, you have to take one, and if you have two qubit states, you need to take 1 2. So 3 qubit states are there, 1 2 4, like this. That means 2 power 0 to 2 power n, you have to take the decimal values. Next, whenever you have a single quantum gate, let us say this is a single quantum gate, and let us suppose this is 1, then you have to take it as u of 0 comma target. Here target is 1. Now if there is a one more state, let us say 2, then how to do this? You have to add, so that is a 2 comma 3. That means these are the operations of that operator u. Okay, and for example, if you have uh, something like this 1 2, and this is, let us suppose this is the head mod operator, then how to write this? H of 0 comma 2, because it is on 2, and you have to add the remaining 1, that is a h of 1 comma 3. So that means this circuit will create a superposition of 0 and 2 and a superposition of 1 and 3. And one more thing you have to remember, always first numbers are off state and second numbers are on state, are in on state, right? Okay, fine. So all these things we have already explained in that lecture, that is solving any quantum circuit by using a new method, right? Now let us come to this Deutsch algorithm circuit. So this is the circuit we have already explained earlier. By using binary notation we have solved. Now let us try differently. Okay, so here the head mod operations, that is in quantum parallelism video I have explained this. Now here we have H tensor 2 operating on 0 1. So what I have explained, so this is LSB, always I will take the bottom one as LSB. Okay, right. So what I have explained, whenever you have 0 starting one, LSB starting one as a 0, then you have to start with the plus plus, double plus, and if you have 1, you have to start with plus minus. Okay, this is the starting. After that, if 0 came, you have to repeat the earlier signs as it is. If you get 1, you have to multiply with the minus extra. Let us see. Now here we have first one 1, that's why plus minus, let me write here, and the next 0 repeated, so that's why earlier things whatever you have, write all the things as it is. So these are the phase factors actually. 1 over root 4, four terms are there, that is a 0, minus 1, plus 2, minus 3. So that's it. So this is your H tensor 2 operates on this initial state 0 1. After that you have this oracle UF operation. So what is, how to operate this UF? Now see carefully, this is 0 means, how you got this 0 here, this is a 0 plus 0, 1 0 plus 1, 2 2 plus 0, 3 2 plus 1. That means here off, first one I'm talking about the control, this one off, and here also off, but for 2 it is on, for 2 it is on. So that's why once you have applied this UF operator, okay, so let me write here, this is H tensor 2 0 1, one more time I'm just taking this. First listen this, and then one more method I will explain, that is also a very interesting one. Now here we are operating this UF. So 1 over root 4, so here control bit is off, that's why I'm taking here minus 1 whole power f of 0 0, minus, again here also off, minus 1 whole power f of 0 1, plus minus 1 whole power f of 1, because it is on, here it is on. Okay, so that's why I've taken f of 1. So 2 minus, again for 3 also it is on, minus 1 whole power f of 1, 3. So on means I am taking it as a 1, off means let it be 0, something like this. Still, if this method is not understanding, I will explain one more method, so no need to worry. Okay, so now here we have to take the options. What about your f of x? Now I am taking, so two options. Let us suppose f of x is balanced or f of x is constant. So what is the meaning of f of x is balanced? Here we have f of 0 and f of 1 output. Okay, so then balanced means you can take f of 0 equal to 0 and f of 1 equal to 1, or f of 0 equal to 1 and f of 1 equal to 0. Any one thing you can try. The first one I will explain, the second one you please do it. I am explaining this. Now just take it and substitute, it's not at all difficult. 1 over root 4, so this is a 0 only, because minus 1 whole power f of 0, f of 0 is a 0, f of 1 is 1, okay, minus as it is. Now f of 1 is 1, that's why minus 2, f of 1 is 1, that's why minus of minus plus 3. That's nice. Now here the most important. Now head mod operation is there. So what is a head mod operation? It is on 2. So that means I am writing here head mod 0 comma 2 h, and you have to add 1 comma 3. What is this technique actually? By using this technique we can write the operations, what this head mod operator is doing. So here actually it is a tensor product of h tensor I. Okay, so without doing all those things you can say simply the operation like this. Now see h 0 comma 2 and 1 comma 3. Okay, so remember always first one is off, second one is on. Now here I have 0 minus 2, h of 0 comma 2, it creates a linear superposition. 0 will become 0 plus 2, 2 will become 0 minus 2. These things already explained in that quantum circuit video. I request you please watch that video. Then you will understand this technique. If you want to learn this technique, learn, otherwise, okay, it's okay, no problem. So 0 minus 2 means on. Here, which one is on? 0 and 2, 2 is on. That's why cancel. Now you can write 2. Now don't bother about that normalization constant, leave it. Next after that minus, if I take minus common, I will get 1 minus 3 here, 1 minus 3. Again 1 minus 3, that means on. Which is on? 1 and 3, which is on? 3, 3 is on, 3, that's it. No need to operate, just by seeing that operation you will get that answer. So you have two states, that's why it is a 1 over root 2. Fine. Now I am converting into binary. Okay, so this is nothing but 1 over root 2. So 2 is a 1 0. After doing the algebra, finally I am converting into binary only. So now what is a common here? 1 is common. So 1, if I take a common, this is a 1 over root 2, 0 minus 1. So which is 1 minus. So if I make a measurement on the second one, that means the second means here, first one, at the top one. So then if I make a measurement, I will get this one. If f of x is balanced, the result, the output is 1 minus. Here we are getting minus and this will be 1. So you can try this one yourself, okay? Easy only, not at all difficult. Let us suppose now f of x is a constant. F of x is constant means both f of 0 and f of 1 takes the same value, that is either 0 or 1 you can take. Any one thing you can take, it's not an issue. Now I'm taking this, both are zeros, substitute, then no change, no change. Okay, minus 1 whole power 0, no change. So that's why this is a finally 1 over root 4. Please remember this word, no change. So f of x is a constant, you need not to operate anything. That means the oracle is simply identity operation. 0 minus 1 plus 2 minus 3. Now still not understanding, now let us apply the head mod operation. So the head mod operation is h of 0 comma 2 and h of 1 comma 3. Now please observe 0 and 2, we have 0 plus 2. So that means off, which is off, 0 is off. That's why 0. Next I am taking minus common, then I will get 1 plus 3, again plus 1 plus 3. So that is of 1. Remember, these are not binary. Okay, so decimal state notation. So now I am converting into binary because the algebra is over. So 0 0 minus 0 1. Now I can take common, that 0 out. So 1 over root 2 0 minus 1. So this is nothing but 0 minus. So f of x, if f of x is a constant, we are getting the first qubit as a 0. So here you are getting it as a 0. So you will get a 1 here if f of x is balanced, a 0 here if f of x is a constant. Okay, fine. Now let us do the same problem by using another method. This is quite interesting. Here we'll talk about this oracle. What is this oracle? How to construct this oracle. And now this is the tabular form. Earlier I have already given in this quantum parallelism video. So I request you please watch this. Right. So this is nothing but a phase factors also. Phase factors and as well as a H tensor to, parallel operation of head mod operator. So here we have 0. So we can write it as 0 0 0 1 1 0 1 1. I'm writing in the binary form. So first one is a 0 plus plus, next again 0, repeat. First one is 1 plus minus, next 0, repeat. First one is 0 plus plus, next one is 1, repeat with the minus sign. That means extra minus sign, that is minus minus. So here 1 plus minus, again 1, repeat with extra minus, minus plus. Now carefully observe. Here we have this input, that is a H tensor to 0 1, which is nothing but H tensor to 1, because 0 1 decimal state notation is a 1. So now observe this one. So this is nothing but H tensor 2 operates on 1. So you got plus minus plus minus. Earlier also we got the same thing. So from the table we are writing here. So this is nothing but 1 over root 4, because of 4 states are there. 0 minus 1 plus 2 minus 3. I will write here. So 1 over root 4 plus, that is a 0, minus 1 plus 2 minus 3. Right. Fine. After that, UF. So here I am explaining this oracle. What is this oracle function? Now I am assuming this f is, let us suppose I am assuming f is a balanced function. Okay, because f is a constant, I already discussed. Here no need to apply anything, it's simply identity. So here we are talking about f is a balanced. Okay, so let us suppose f of x is a balanced. So I am assuming f of x is balanced, I am proceeding. If I get that result, f of x is balanced. If I didn't get that result, so f of x may be a constant. Right. If f of x is balanced, then what is the oracle? Let me explain. So the oracle is given by 2 qubit states are there. It's simply a C0 operation. That's it. So this is 1 and 2. I have already explained, okay, earlier what is the decimal state operation. So this is nothing but x of from where to where, 2 to 1. That's why 2 comma 3. That means it flip 2 and 3. That's it. So by using this oracle operation, so this will become 1 over root 4, 0, minus 1. See, 2 become 3 and 3 become 2. Right? So now carefully observe this. I am just rewriting this 1 over root 4, 0, minus 1, minus 2, plus 3. This is quite interesting. Please listen. Now carefully observe this. In this table where you have this signs plus, minus, minus, plus. I think here we have. So finally here we will get, sorry. So this is nothing but H tensor 2 operates on 3. So now this finally this is equal to H tensor 2 operates on 3. So just I am writing that. I hope everybody understand. This is nothing but H tensor 2 operates on 3. So right now we have completed up to this. Still we have some head mod operation, don't get tension. Now I'm going to write this 3 in the binary notation, that is 1 1, we know that. So I'm taking this as H tensor 2 1 1. Now see, I can write this as H operates on 1, tensor H operates on 1. Okay. Now I'm not doing anything with this first one. Okay, just a second one. I'm writing it as a that diagonal state, that is diagonal basis, that is minus. So this is nothing but H1 minus. I hope you understand. Now I'm talking about that head mod operation. So actually here we have this head mod operation. So this one, that is a H tensor I. So now, so with this H tensor I, so the H will operate on the first one and I will operate on the second one. So this is nothing but H square 1 minus, which is nothing but 1 minus. So this is when f of x is balanced. So I hope now you understand what is the oracle function corresponding to this f of x is balanced. This is simply C0 operation. If you get one output here, you will confirm that the function is balanced. If you didn't get one, you will say f of x is a constant. Okay. So this is an alternate way. What I have observed is if a function f of x is balanced, we are getting the last one always in the table. That's why this table, phase table, is very crucial. In the next algorithms also we will use this table by using this table we can solve that circuits very easy. See, here I am just solving the quantum circuit by using the decimal state notation. For the algebra I am using that decimal state. After that finally again I will convert into binary and I will do that. Okay. So that's it. I hope you understand this, and if you have any difficulty, so please let me know. Okay. So thank you, and we'll meet again in the next video.